Hello, my name is Boyd Vallis. I'm the coordinator for CHaMP, and I'm here to talk to you today about how we're converting measurements, the data you collect in the field, and how we turn those into metrics and how those metrics feed into different models that we're using within CHaMP. So I first wanted to talk about the CHaMP process and where you fit into this whole process. I see it as a life cycle, a yearly life cycle sort of thing. So to begin, the protocol development, usually we go at the end of the field season, assess how field implementation went and look at the protocol and make sure all the data we're collecting is repeatable and robust, and make changes accordingly if we see some weakness. In the spring, we developed study designs, and we'll chat a little more about that later, but basically you'll all be working in different watersheds, and you'll be sampling sites within those watersheds, and those watersheds are part of a larger study design element. Training, this is where you're beginning this week, and this is where you'll spend 8 days conducting CHaMP surveys, learning the different methods, and you'll be walking through different modules and going through post-processing and really figuring out how to conduct a CHaMP survey. In the summer, you will be doing the data capture and data management, and that will go till the fall, and then in the fall you will conduct QA, QC of those measurements and then generate metrics. We will generate metrics which will also go through a QA, QC process, and then that data will be used to feed into different analyses, different models, etc. So to begin, what you're doing, we call those knowledge products. Those are the data and observations in their raw form. So that's things you'll be collecting in the field that are important to fish. And then again, how we take that data and derivatives of the data you collect and create different metric elements. Those could be water depth maps, digital elevation models, large wood counts and frequencies and volumes, and then how those then feed into the different models we're producing within CHaMP. And really those are the 3 elements I'll be discussing today. So measurements, those are the fine scale descriptions of the physical, chemical, hydrologic, geomorphic, biological characteristics of a stream. And those are taken at a CHaMP site. And within that CHaMP site we have channel units, we have transects, but everything you'll be collecting, we're calling those measurements. So within a given year, the CHaMP field season, this is an example of last year, we're collecting lots and lots of data. So we had 22 crews, 124 hitches. A hitch usually constitutes 4 to 5 sites. So within a given year, it's roughly 500 surveys. Each survey has about 393 files. So a lot of data. And overall, by the end of the season, there will be close to 200,000 records, different data types, and uploaded from your tools out in the field to your computers up to CHaMP monitoring. So how do we measure sticks and stones? Well, you guys will be going through the 8-day training, and we have a standardized protocol. We have trainers that will teach you 4 hours at each module, where we'll teach you how to measure substrate, large wood, everything considered important to fish. So the training is a large component of the robustness of our program. So within that, each site that you'll be sampling is 20 times the bankful width. So if you have a bankful width of 10 meters, your site would be a 200 meter site. So within a day, you can sample that 200 meter site, and throughout the season, you'll sample roughly 25 sites. And then throughout the different years, those sites will add up, and we get typically around 47, 48, 49, 50 sites. So there's really two forms of data collection tools. The iPad, which we collect the auxiliary data information, and that's going to be capturing those that list of things below here are the channel units down to the pebble embeddedness and riparian, etc., discharge. And then that total station is what you'll use to conduct the topographic survey. That data is then passed from those instruments. You'll also have stream temperature. You'll be collecting solar pathfinder data, sun eye data. We switched those. And that data will all go into your laptop, which will then be uploaded to CHaMP monitoring, and then the QA/QC process will begin. But before that happens, we want to just briefly talk about, that when we're collecting ecological data, there's lots of things that can create noise and lots of things that can obscure the answers. So we try and reduce that as much as we can. We try and reduce that source of variability. And there are different elements we can control. There's the protocol, which we have fine-tuned, and we haven't made a change in a couple of years. So we feel that that protocol is very tight at this point. The training, this is the 7th year of training. We have it pretty well developed, where we feel as though we can train you in the best possible fashion so that you're ready to go out into the field and start collecting data and doing it in the same fashion. All crews, all people. And we try and avoid the protocol drift. That means once you leave training and you've learned how to sample and you think you understand the different sampling techniques, we want to make sure you continually use that protocol to ensure there's no drifting of what's in there, so that again we have a repeatable data set coming in. And then equipment, we provide you with the most up-to-date technology and use equipment that's the same throughout all the basins, so we know that the data is all comparable. So those are all the things that we can control to ensure there isn't protocol drift or equipment malfunctions or issues with training, etc. So, the next slide here is more of illustration of the process of how we ensure data quality within CHaMP. So, basically the data coming in through the iPad, that data logger application, then goes into that laptop, and before it goes to the laptop, we have some QA/QC components built into the iPad that basically maintains consistent data being entered. So we know if there's values out of range, we'll highlight and let you know those values are out of range. We'll let you know if there's data missing. So basically, at the end of the day, when you leave the field, your data is complete and within proper range. That data then gets transferred to what we term the data broker, and that is a quality control element as well, where we look at the format of the data and the schema of the data coming in, the completeness of all those files. And then once it goes from the data broker, it goes up to CHaMP monitoring, and another QA/QC component is implemented where we review the number of records, review outliers, give you nice graphical ways of assessing if a data point is out of range, and really just some sanity checks to make sure that everything you collected makes sense. And you're able to plot that and look at that compared to all the other data. So once that QA/QC of that raw measurement data is done, then things will go into up to the metric generation. So this is just an example of a graphical display of temperature QA/QC checks. So this graph basically shows an outlier here and highlights it, and then you have to go in and assess whether that's a real value or if maybe that temperature probe was removed from the water for a few moments to be checked by the crew, and that's why you have this spike in temperature. So it's really a useful tool, and it really helps with the quality control of all the data. So again, this is a fine-tuned graph of how you guys will be moving throughout the season. So that basically those logger checks in the total station, you'll be post-processing through the CHaMP Topo toolbar, uploading that data to CHaMP monitoring. Then in September, October is when we start that QA/QC of the data. So you'll be working on that in the postseason, and then the metric generation and review process, which will then proceed to the analysis phase, which will then, once the analysis is conducted, then people can work on generating reports. So I explained what measurements are, and now metrics are basically a derivation of those raw measurements, combining sets of relevant measurements and trying to characterize different aspects of the stream. And for instance, we will tally up the total number of large wood within the stream that meets our wood criteria, the number of pools per 100 meters. All these things are relevant to fish, and we look at how they're changing through time. Are they improving, degrading, maintaining? What's happening at a particular site and within a watershed? And we really use three basic criteria for whether we keep a measurement or a metric, and that is information content. Is that information related to cell-mounted productivity, including survival and growth? And data form. Does that data provide robust statistical information and data quality? Can it detect heterogeneity? Is it repeatable? These are all important questions. Then the feasibility component is that data collectible within a day, and is it are we able to use the tools and software that are currently available and affordable to do so? So that's the feasibility aspect. So you go from the knowledge products, the measurements, to the metrics, the comprehension products, and you're generating those digital elevation models, those water depth maps, those D50s, which is the median substrate size. So all these things are important aspects for answering our fish habitat relationship questions. So these metrics, we try and ensure that these metrics are capable of doing this, so avoiding bias and noise, and that we can look at those spatial and temporal variance patterns. And then, since these metrics are collected in a systematic fashion and using a study design, we can then extrapolate that data out to the larger watershed. So how those can feed into from the metric stage to the models, which will be used for analysis and summary products. So really, these graphical tools that we use to visualize the different metrics, so we can look for patterns of measurement, noise, and variance, both spatially and temporally, is very important for us in terms of making sure we're producing high quality products. And one way of doing that is we do repeat surveys in which we have multiple crews go to the same site and see if they get the same answer. And we compare those answers and determine, is there too much noise in that data? Meaning, what Joe collected versus what Mary collected, is it the same? Is it different? And so that those magenta colors, the ones on the right, that's the variance in measurement noise. And those are the ones I talked about are ones we can control, or as much as humanly possible. And that's, the smaller that magenta, the better. So you see how we have that for all the different metrics we're generating. So very insightful, and this is what we use when we make any changes to a protocol, or maybe we decide to drop a measurement because it's not repeatable. So this is a good way of assessing that. And then once we have that, since all the study designs within the different basins that you're working in are done in a similar fashion, and all the data you're collecting is using the same protocol, we can compare through space and time the differences in the different metrics. So I can compare the Yankee Fork coarse and fine gravel values to the Intiat or the John Day, etc. This is illustration of the river bathymetry toolkit output, and this is cross-sectional information that we've developed an automated toolbar that calculates what's the distance from the red, which is the right edge of water, to the blue, the left edge of water. And we can look at widths, we can look at depths, we can look at lengths, we can look at sinuosity. There's a lot of metrics that we can generate and automate from that topographic survey. So a really robust tool. These are the different metrics and measurements I was just discussing. So, each one of these can be used to address ecological concerns, things that might impact salmonid and steelhead habitat. So, very important for us to assess the change of habitat through time. So this is really the uniqueness of CHaMP is illustrated here in that we can combine that topographic data that you collect using the total station and integrate that with the auxiliary data collection. So we can look at volumes of pools and how much wood is within that pool, or what is the density of wood, or there's just a lot of different ways we can combine that data to really look at things in a different light. So again, this is really looking at how those metric timelines for our metrics when we determine, are those metrics giving us enough information? Are there different metrics that could be more insightful? How do we document those? And this is that timeline and locations of where we document that, the metadata associated with it as well. So these are when we're on CHaMP monitoring, we can track what you guys are doing throughout the summer. So we know how many sites you've sampled, how much data has been uploaded, how many topo data elements are uploaded versus auxiliary versus stream temperature versus photos. So if we see that there's issues with the topo data being uploaded, but then you have all your auxiliary data uploaded, we can give you a call and say, you need help with something, and really stay on top of things and know where you guys are sitting so that we can get through the field season in an efficient fashion and help you guys get to your end goal of publishing that data. So again, this is this building process, the measurements to the metrics, now the application products. The application products are those different models, the habitat suitability models, which we measure carrying capacity or look at geomorphic change detection, or we develop hydrologic models that also feed into those habitat suitability models. So really a lot of cool tools and products we're developing from the data you're collecting. So that's why it's so important for you to collect high quality data, so we can look at that change through time. And this is just a cartoon that gives you an idea of that different data and the different metrics that it feeds into and the different models. So just another way of assessing or visualizing the data. This is an example of our hydrologic model, and we use pretty proud of this. We're taking the topographic data with the data you collect, the discharge data as well as the substrate data, and we combine those and run it through the 3D Delft model, and we can give a flow model of a particular site using the DEM and that auxiliary data. That hydrologic model can then feed into a habitat suitability model, which we're assessing carrying capacity at a site, and we're using surface roughness and that hydrologic data, model data, and we're able to say how much habitat is available to fish at a particular site for a particular year. So we can look at pre-habitat restoration and post-restoration. So really important to determine whether restoration is being effective or not. So these models are then used to determine really is we're trying to reach the holy grail of, if we're producing more habitat, are we producing more fish? So trying to show that relationship between fish and habitat. So that's about it. You guys are the foundation. You're the building blocks for this process, and so go out there, collect good data, have a good time, and enjoy your summer. Thank you.